let's take a look at differentiation. Again, differentiation is the process of finding the derivative. I'd like to remind you one more time. So we're going to learn how to apply the derivative in real life scenarios like velocity, acceleration, and other rate of changes. So first of all, let's take a look at the rate of changes, which is the main focus of this particular section. So far we have seen how derivative is used to determine slope. And derivative could also be used to determine the rate of change of a variable with respect to another. Applications involving rate of change occur in a wide variety of fields. A few examples are population growth rate, population production rates, water flow rates, velocity, and acceleration, which is the focal point of this particular section. The common use for rate of change is to describe the motion of an object moving in a straight line. In such a problem, it's straightforward to use either a horizontal or vertical line with a designated origin to represent a line of motion. So movement to the right, upward or right is positive. It's considered to be positive direction. A movement to the left or downward considered to be negative. Okay, negative direction, and it's pretty consistent with the XY coordinate system. Cartesian system, right? Okay, the function S that gives the position, so we call the position function of an object as a function of time is called a position function. So position function F is basically a function of the position at a time t. If over a period of time delta t, the object changes its position by the amount delta of x, which is s of t plus delta t minus s of t, then rate is equal to distance over time. This is what they speed, right? Refer to speed. Speed is just a term with no direction. It's velocity with no direction. Without direction. So that's the difference between the speed and then velocity. The velocity is the variable term with the direction. The average velocity equals to changing distance over changing time, which is delta s over delta t. So that's the definition of average velocity. Okay, let's say if a ball is dropped from the height of 100 feet, its height s at time t is given by the position function s equals to negative 16 times t squared plus 100, the typical position function, where s is measured in feet and t is measured in seconds. Find the average velocity over which of the following time interval. So this is between first second and second and the second. The second problem is between 1 second and 1.5 seconds. Third one is between 1 and 1.1 second. For the interval between 1 and 2, the object falls from the height of s of 1, position function at time t equals 1. Position function, position at time t. This is position function at time t equals 2. Position at time t. So the position s is 1, which is negative, replace x with 1, so you get negative 16 plus 100 equals 84 feet. Okay. S of 2, at the second second, we get negative 16 times 2 square plus 100, which is, this is negative 64 plus 100, give us 36 feet. So the average velocity is equal to delta x, change of the position over change of time, right? So 36, notice that we use 36 minus 84 over 2 minus 1 becomes negative 48 over 1. So it's negative 48 feet per second. So that's average velocity. Notice that the answer is negative. And that means it's going downward, right? Only if it's going downward, then your velocity is negative. Okay. For the interval between 1 and 1.5 seconds, the object falls from the height of 84 feet to a height of 64 feet. The detailed calculation looks like this. S is 1, negative 16 times 1 square plus 100, which is equals to 84 feet, right? Second one is S 1.5, which is negative 16 times 1.5 square plus 100. And this is actually negative 36 plus 100, which gives us 64 feet. Now we find the average velocity using change of distance over change of time. Using 64 minus 84, that's a change of distance. And 1.5 minus 1, that's a change in time. So it becomes negative 20 over 0.5, give us negative 40 feet per second. Again, this is negative, meaning going downward still. And from the context, we know that it's going downward. The ball is going downward. For the interval between 1 and 1.1, the object falls from the height of 84 feet to a height of 80.64 feet. So S is 1. From previous, we know that is 84, right? S of 1.1 is negative 16 times 1.1 square plus 100. That turned out to be 80.64 feet. Then we apply the average velocity formula. 80.64 minus 84 over 1.1 minus 1. Turned out to be negative 3.36 over 0.1. It gives us negative 33.6 feet per second. Again, it's still going downward since it's negative. The average velocity are negative, indicating the object is moving downward. Okay. In general, if S equals st is the position function for object moving along a straight line, the velocity of the object time t, v of t equals to limit when delta t approaches 0 for function s of t plus delta t minus s of t of delta t equals to s prime of t. So this means that velocity function is the derivative of the position function. It's the derivative of the position function. Velocity could be negative, could be 0, could be positive. The speed of object is the absolute value of this velocity, meaning it's velocity without a direction. and speed cannot be negative. Okay. So this is the key thing, right? Definition of the velocity function using the limit definition. The position of a free-falling object neglecting air resistance under the influence of gravity can be represented by the equation S of t. S of t represents position function. Position at any time t equals half times g times t squared plus v0 times t plus s0. So where s of 0 is initial height or initial position, initial height of the object, v0 is initial velocity of the object, and g is the acceleration due to gravity. And on Earth, the value of g is approximately -32 feet per second. It's the same thing as -9.8 meters per second. Okay. Per second. Okay. Per second square. Okay. Now we can use this to, you probably learned this in physics, and we can use it to calculate some real problems. At time t equals 0, a diver jumps from the platform diving board, and that is 32 feet above the water. The position of the diver is given by S of t equals to -16t squared plus 16t plus 32 position function. Where S is measured in feet, t is measured in seconds. So this is a picture describing the motion, right? When diver jumping into the water. When does the diver hit the water? Think about this. When diver hit the water, position function S of t. When you hit the water, then S of t equals 0. Okay, and you can use this to solve for the time t, right? And what is the diver's velocity at impact? Velocity function equals to derivative of the position function, which is -32t plus 16. Then once you find out the time t equals how many seconds, you'll be able to find out the velocity when diver hit the water. Okay, so to find the time t when diver hit the water, let S of t equals 0 and solve t, right? So we have -16t squared plus 16t plus 32. This is S of t, set equals 0. Here you can factor out -16 t squared minus t minus 2 equals 0. And inside the parentheses, the quadratic equation, so we can factor as t minus 2, t plus 1 equals 0. And we use the zero factor properties, setting t minus 2 equals 0, setting t plus 1 equals 0, and solve t. First equation, add 2 from both sides of the equation, t equals to 2. Second equation, subtract 1 from both sides of the equation, t equals to -1. And time t equals -1, this is not a realistic answer. We don't know what is -1 second, not realistic. So must be excluded, right? So we get rid of this. So time t equals 2, meaning after 2 seconds, the diver will hit the water. Okay. So the velocity function when the diver hit the water, v of t equals to derivative s f prime of t Let's run this with negative 32t plus 16. Now here we just replace time t with 2. So it's negative 32 times 2 plus 16. Negative 64 plus 16, which gives us negative 48 feet per second. Okay.